Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, this is our second video of job sequencing. In the first video, we talked about the n jobs on two machines, and in this video, we will talk about the one more example where we have those conflicts when we want to find the minimum and we have a ties, and we're going to see how to deal with that. And also we will have the m jobs on the three machines. Okay, so we saw many things in it, like basic terminology. In a basic terminology, uh, one second, where's the mouse gone? Okay, in the basic terminology we see a lot of things, and we see the no passing rule. And this is the question of this video for you, that what is this no passing rule? Write in a comment box what is this no passing rule, which I explained in the last video. You can also read it from here. I will also send this PDF to you guys. Okay, and you have to tell me in your own words what have you understood from no passing rule. This is the question of this video. Then we have seen the principal assumptions. What are the assumptions we have? And with that, the types of job sequencing, that depending on how many machines you have and how many jobs you have. But we had to got to do first two. There's n jobs to be processed on two machines, which we had done already. We will do one more example for it, and on the three machines, if n jobs are to be done using the three machines. Okay, and then we saw that the competition to calculate n jobs on two machines is very high, and we have what is called as the Johnson's algorithm, actually developed by Johnson and Bellman, right? So what is the Johnson's algorithm is we want to select the AFIs and BFIs, the minimum among them. Okay, and in AFIs and BFIs, if it is ARR, AFR, which is smaller, then what is this AFR? If you're still confused, I will explain it from this. And if we have BFS smaller, then that's a job at the last. If AFR is smaller, then RF job first, and BFS is smaller than SF job at last. What does it mean? So let's see from this example. I will make you understand what does it mean. Say when we are serving a particular, so this is my AFI and this is the BFI. That means I have to serve this, and go on. This is a loop of I. Okay, and when I go into it to find the minimum, I will call it AFR. Okay, and if AFR, and for this I call it BFS. Okay, I increment S as 0, 1, 2, 3, 4, and so on, or 1, 2, 3, 4, 5, and I increment R. This is A subscript R. R as, that means A of 0, A of 1, A of 2. So R goes from 0, 1, 2. Same is with the B of S, and S goes with like 0, 1, 2, so on. B of 0, B of 1. So say this is B of 0, this is B of 1, this is B of 2, this is B of 3, and so on. So in AFIs and BFIs, AFI means all of this and BFI means all of this. If in that AFR, that is any R, 0, 1, A of 0 or A of 1, A of 2 is minimum, if that is minimum, in this case 2 is the minimum, right? And we have to see it from both AFIs and BFIs. That means all of this. If AFR is smaller, then that goes as a first job from the left side. But if BFS is smaller, then that SF job is put on a last. That is what we have, this thing. And then we said if you have ties, for example, then what could be the ties? Tie could be between the AFIs. The tie could be between here, in between the AFIs. Okay, say for example it was 2, it's also 2. Then you need to select, you can select any one 2. You can select either this job or you can select either this job. It doesn't matter, right? Because they are same. So it's your choice, whatever you want to select. This is the one scenario. Second scenario will be that this tie is not between this, it is between these guys. Okay, so you can choose, if this is tie 2 and 2, so you have to put any 2 here. Say for example you put up this job 2 here or job 5 here. That's your choice. Say for example I chose the job 5 if it is tie between these. if there's a tie between B of i's, say for this is 3 and this is 3, you can choose either job 5 or job 1. That's your choice. So that is to be done on the top, on the last, because B of i's has to be assigned last and A of i's has to be assigned as a beginning, in the beginning, okay, from this way forward, and B of i's has to be processed this way forward. Okay, that means they are to be served last, right? Then third thing will be, if there is a tie between these two, A of I and B of I, there is 2 here and also 2 here. For example, say this was 11 whatever, but 2's are common. A is also 2, so both are smaller and both are same. So what should we do? In this case, you assign both. You assign 2 to the front and this job to the back. So this is how we do that. So let us see how we do these things in an example. Okay, so this is our example. A bookbinder company has 1 printing machine and 1 binding machine. So I got 2 machines here, and jobs could be many, but machines gotta be 2 for this scenario. So there are manuscripts of a number of different books. Processing time for printing and binding are given in the following table. So printing and binding, there are 2 machines here which do printing and binding, and we have many jobs like A, B, C, D, E. These are the manuscripts of different books which we have to print and bind, and we know the printing takes this much of job, binding takes this much of job. But we should understand here one thing, that we have to do for a manuscript, we have to do printing as well as binding. But the thing is that, for example, you're printing, you will not do binding at that time, right? So you have to wait when the printing is done. So you have to assign the jobs in such a manner that this binding has to wait for printing, right? Because the scenario is in the form of A, B. If this is, say for example, P and this is B, so it is like PB. We have to do first printing, then binding. If there is no printing, how can you bind, right? So binding has to be after printing. But the question is, if you're trying to assign the job of a manuscript same time binding and printing, so binding has to wait, right? Now we have to do something to minimize the overall waiting time, so that the overall time of printing and binding all these manuscripts are minimized, because there are different time slots. Okay, because there is 6 times and 9 time. So if we do it just randomly, it will take there will be a lot of wastage of waiting time. So we have to assign intelligently, so that there will not be any wastage there can be little wastage in waiting, but not too much. So we have to maximize it. Okay, we have to put up the optimum sequence. So for that we will use the Johnson's algorithm, but in this case I am seeing that there are something. Let's see how we solve it. Okay, so when we try to solve it, we got to see from the A of i's or B of i's. This time it is P of i's and B of i's. Okay, is P of R smaller or B of S smaller? Who is smaller? Okay, and definitely when I scan all of these and I'm seeing P of R is 1, that is smaller. So I gotta assign the job B in the front of the queue and remove it from the table, because I have assigned this. Okay, so my left out table will be like this, that is 5, like B is gone. Now I have the A, C, D, E, right? This is the next table. So I have to again try to see which job is smaller. I'm scanning 5, 9, 3, 10, 2. Oh, okay, 2 is smaller in all of this. So I gotta assign 2, but when you gotta assign 2, that has to be done in the last, because I cannot do the binding without printing, right? So therefore this has to be done on the back of it. So that's why I assign binding on the back of it, okay, on the last. So assign this job A on the last. Okay, but the way I'm doing this will minimize the waiting time if I see the minimums and assign it in this fashion, which is given by the Johnson and Bellman. Okay, so when this is done, so this is gone, the table will be only C, D, E, right? This is gonna be my table. Now, who is the smaller in this? 9, 7, 3, 8, 10, 4. So 3 is smaller definitely. So I have to assign 3. That is D. Because it is from this column, so this has to be an upfront. So D is put up here. So after B, I will put up D here. okay, and delete it. Now after that, what will you do? Who is smaller now? Is 10, 4, 7, so 4 is smaller, so that means E has to be put up on this side, okay, and clear it. Then C is left out, that is here. So my will sequence, optimum sequence will be BDCE, right? Then I have to assign them and see the total time here. Now if you see here, we have to assign the printing first, okay? So we will try to have, we have a, what's our schedule? Let me write that also. That is my the sequence is like BDCEA, BDCEA. This is my schedule. Let me check it if it is that only or not. Yes, BDCEA. Okay, so okay, so this is my optimum sequence, BDCEA. So what I'm trying to accomplish here is now that printing is to be done first, in first the B, then D, then C, then E, then A. So B starts, definitely will start from the 0 because it's the first job, so it starts from at the time 0, okay. And then after that, uh, we have to see what's the B total time, that is 1, so it will end at 1, okay. The next job, that is D, has to start it after the 1, so this is 1 starting at the 1, it finishes at 1, D starts at 1, because we don't want to make printing to wait. We give one after other the jobs, so D is to be given. So D is having 3 time, so 3 plus 1 plus 3 is 4, so it ends at 4. So next job starts at 4, that is C. The job C has to start at 4, and C has the value 9. Processing time is 9, 9 plus 4, that is 13, so it finishes at 13. So E will start at 13, okay, and E is 10, so 13 plus 10 is 23, and after that it start A, the last job A starts at 23, and A is of 5 units, I guess, okay. 23 plus 5 is 28, so I am done with the A. Now I start binding processes simultaneously, try to see. And because if you try to do B, because we have to assign these, sequence is the same for the binding as well. So if you want to bind at the time, but at that time B you want to bind, it is a 0 time, both binding and printing will come at a 0 time. At 0 time, the B is in a printing job, so I cannot bind it unless it is not finished, so I have to wait one time unless it doesn't finish. So whatever is the timeout of the first job, that is for the waiting time, that is the waiting time all the time added to the second binding job, right? So you have to wait this much, so one times you have to wait, right? Okay. Now after that, the B on the binding takes 6 units of time, so 1 plus 6 is 7. So the next job will start at a 7, and I'm seeing the D is already printed at 4 units of time, so this was 4 p.m. And here 7 p.m. binding starts, so it doesn't have to wait, start at 7, not a problem, there's no waiting done. So for the D, it takes 8 units of time, so 7 plus 8 is 15, okay. And I'm seeing now it will try to do the C after D, it will try to do the C, B is done, D is done, now it has to do the C. Now C finished at 13, and I'm free at 15, so I don't have to wait again because C की printing हो चुकी है. I have to now bind it, which is finished at 13 units of time. So let us go it for the 15. Start from the 15. So 15 plus whatever the C takes for binding is 7 units. 15 plus 7, that is going to be 22. Okay, and here if I started at 22, because I am finished at 22, now binding machine is free at 22, but the E is undergoing printing at 22 now, because it finishes at 23 hours. So we have to wait 1 more hour here, we have to wait 1 more hours because to finish printing so that I can bind. Okay, so it starts from 23, and E has the 4 units. 23 plus 4 is 27, so it finishes at 27. So now it is ready to go for the binding of manuscript A, but manuscript A is undergoing printing. Not at 27 I'm free, but I cannot go for binding because it is undergoing the printing. So I have to wait one more time. Okay, so I will start at 28 and 30. So these times are to be added in my waiting time. Okay, the idle time or waiting time for the binding process. So total time of printing is 28 and I'm finished at 30. So printing and binding and totality printing has to wait last 2 moments, okay, so that I can say I'm finished. So for machine A, that's printing 28, 30 minus 28, that is 2 hours will be waiting time for that, because at the end it has to wait for binding to finish. But for the binding there will be the waiting time. The first will be the whatever is the timeout of the first job, that is to be added. So 1 is added. Then the next job, that is 7. Let me clear it first. Let me clear the clutter to do it again. So this one is already added here. Then the next is the beginning time of the second machine, the binding machine, and the finish time of the I-1 job, that's 7 minus 7. Okay, for this case 15 minus 15. For next case 23 minus 22, that is 1. Okay, and for next case 28 minus 27, that is again 1. So total time will be 1 plus 1 plus 1, 3 hours binding time, waiting time for the our idle time for the binding machine. Right, right. Now this is the another example. Here I got a 7 jobs to be processed, but in this scenario I'm having again it's a machine A and machine B in order AB. That means you have to first do the A, then B, like printing is to be done first before binding. Okay, जब printing नहीं किया तो bind क्या करोगे ना? It is like that. But here I'm having something common. Okay, I'm having common, like 3 is here common between the A and B machine. Now 10 is common between the two, between the same machine. So I can choose from this any one, and like that. Let us see how we fix this scenario. Okay, so I will try to find the smallest. What the Johnson says, try to find the smallest in the A of i's and B of i's, and I'm scanning, and I'm finding the one is the smallest. So that means job number 6, because it's from the second machine, so it is to be assigned at the back. So job 6 is assigned at the back. Okay, that's at the last. So, and when you are done, just cancel it out and try to find now among these who is the smallest. Okay, and I'm seeing it is the 3 is the smallest, but there is a tie between machine A and machine B. Both have the 3, which is now the smallest. So what should I do? So in this case, when there is a scenario, the tie is between it is between the two machines. The tie is between the machine A and machine B. In this case, both are assigned, and this one A in the machine A side, it is assigned up front. Okay, it will assign up front, and machine 3, that is 7, it will be assigned on a back after whatever the slot is free there. Okay, because 6 is already there, so I have to, after that it will be now the job 7. Okay, and job 1 will be up front, and job 7, because it's 3, will be on a back. So we can assign both of these. Okay, the B from the last side and the A from the front side, right? And in the meantime both are assigned, so we had to cancel them out. So left out, this will be my left out now matrix. Okay, that is shown in the next table here. Here we go. So this is my this thing, and now I have to see who is the smallest here, and I'm seeing 6 is smallest, right? 6 is 6 smallest. Yeah, 6 hours. And in this scenario, if you see, the 6 is smallest and 6 is also here smallest. So should I do because now in this case, if you could see, it is the same job 4, okay, where the common comes up. In this case, when there is the minimum job is on this minimum processing time, which I'm trying to find, is with the same job in both machines, then you can do either way. Either you put up this 6 job 4 on a front, or you can put job 4 on a back. So it is your choice. You can go this way or you can go that way. Okay, then you will remove this column, row 4. Okay, and my matrix is now like this, that is 2 3 5, and I'm trying to find the minimum, and I'm seeing now here in this scenario 10 is 3 times. Okay, so there is tie between the A machine and B machine and also the B machine. So from these two I can choose any one, and so I have to assign this to the left side, that is upfront, and this to the right side. Among these, either the job 2 or job 3, that's your choice. So if I have my I have chosen this one from the above, then the 5 job will be here. Okay, and this 2 job will be here. Okay, or if I chosen this one, then the 5 job will be here and the 2 job will be here, and then and you have to cancel them out, and only one row is left out, that is 3 jobs, so that is to be here anyways. So you could have 1 4 5 3 2 7 6 or 1 5 3 2 4 7 6 in this scenario. Then for both of these, these are both are valid now. Okay, these optimum sequencing, and now you have to find the total elapsed time. Okay, if you chose this one firstly, for example, so you have to choose the job 1 first, which starts from 0, and then you see what is the processing time, that is 3 units of time. You just see from the table and assign them. Okay, I will put it here. Now you can see here the machine A, which is the job 1, is to be done first. So that means it starts from the 0 and it takes 3 units of time. So 0 plus 3 is 3. Now after second job, that is the 4th job, is to be done. Okay, the 4th job is to be done, which is taking 6 units of time. So it starts at 3 when you are done with the first job, and 6 plus 3 is 9. Now next job 5, which is 10 units, 9 plus 10 19. So third job will start at 19, and 19 plus 15, that is your 34. So next job starts at 34, that is 2, and it takes 12 minutes of time for the machine A. So 34 plus 12 is going to be 46. So next starts from 46 plus 7 has 9 units of time. 46 plus 9, that is 35. The next job is a 6, which is having 11 units. 55 plus 11, that is 66. This is at the time 66 job machine A finishes its all jobs. Then machine B starts doing job 1 after it is finished here, so we have to wait for this. So 3 units of time is waiting all the time, 3 plus waiting time, and the 3, it takes 10 units of time. Job first, sorry, it takes 8 units of time. 3 plus 8, that is 11. It starts next job up to 11 because it is finished at 9, so we can start at 11, no problem. And the job 4 is 6 units, so 11 plus 6 is 17. So when it comes here 17, it's already it finished at 19, so I have to wait 2 units of time, 17 plus 2, to reach up to 19, because it's already being occupied by the machine A. So I cannot go for the machine B with this job, right? Okay, because there is a no pass. Okay, and using the no pass, it has to finish this job properly, then it can go here to the next job. So 19 is here, so we have to wait 2 units of time. So I can calculate it by 19 minus 17 to get that 2 back. And job 5 takes 12 units of time, so 19 plus 12 going to be 31. So at 31 I could have started this job, but it is already being occupied here, so I have to wait until 34. So 34 minus 31, that is 3 units of time I have to wait it here for this thing. And then this third job takes 10 units of time here, so 34 plus 10, that is going to be 44. So I can come here 44, but it's occupied here. The job 2 is occupied by the machine A, so I have to wait 2 more units of time here until 46, until it is finished at 46, so I can start at 46. And job 2 is 10 units of time. 46 plus 10, that is 56. So here I come at 56, it's already finished at 55, so I don't have to wait. I can start job 7 at the same time, so no waiting here. And 7 is 3 units of time, so 56 plus 3 is 59. When I come here at 59, it's not free, because up to 66 it's not free, so I have to wait 7 units of time here to get the 66. Okay, so I start from 66 and finish it. The job 6 has 1 unit of time, so 67 it's done, so total time is 67. And machine A finished at 66, so it has to wait only 1 unit of time, and this guy has to wait here the 3 units of time, then 2 units of time, then 3, then 2, and then 7. Okay, and same way you can calculate if I have gone for this much, this sequencing. Okay, so for that, this is a table, you can work it out yourself. Okay, and then you will see what is the idle time for the machine B is 17 hours, and for A it is 1 hour. And when you calculate from this and this table, you will see in both cases the total time elapsed time is 67, and for A it has to wait only 1 hour last, and for B it has to wait for 17 hours, because 7 here, then 3 here, and so on and so forth. Right? Right. Now we come to the next part of the question which we are dealing with, that is processing n jobs through 3 machines. So we can use the extension of Johnson's procedures of scheduling n jobs on 3 machines, let's say ABC, and it has an order of ABC. That means C cannot happen before B and B cannot happen before A. Okay, say for example A was printing, B was binding, and C is putting up label on that on the top of the binding. So you agar print nahi hua hai, so what will you put label on? So you need a book first, printed form, and then you also need a binding. So when the binding is done, then and only then you can put up that sticker, the name sticker and tag and all, right? So they are in order A, B, C, right? So as you could see here, processing time on a machine, the jobs are 1, 2, 3 up to n, and there are 3 machines. So this is written, now these machines are on a row side and the jobs are on a column side. We could put it other way also, but now because the jobs are many, okay, we can do it this way, or we can do it that way also, like in a previous example. And then there are these are the processing times, right? So in this algorithm where we have the 3 machines and we have the n jobs, we have to apply the same Johnson's algorithm, but we have to understand that Johnson's algorithm is used for 2 machines only. Now here we have 3 machines, so what should we do? So we use a trick, we use a different method. We extend actually the Johnson's method on this. So how we do that is we convert this 3 machine into 2 machine model. Okay, when you convert this 3 machine to 2 machine model, and for 2 machine model you have already what we have done, we apply the Johnson's rule on it, or Johnson's algorithm on it to solve it. Okay, but can we convert this 3 machine into 2 machine or not depends upon these 2 conditions. Okay, so we have to set if this either of this condition is satisfied, not both. If one of the condition is satisfied, I can convert this 3 machine into 2 machine model. So what is that? Before reading this all, I will tell you how. What is that thing, to make it very simple. So what I do is I find, let me get the pen. I find in machine A, if order is A, B, C, that means B is the middle one. If order is A, C, B, then C is the middle one. Don't think that C is, then we have to combine, the C is the middle one. We have to see that. But if the order is A, B, C, then the B is the middle one. So whichever is the middle one, if maybe the order is B, C, A, okay, then C is the middle one, okay, not the B. So we have to see the order to see which one is the middle one, middle machine. Which one is the middle machine, we will find the maximum of that, and whosoever are the last 2, like we have for example the order ABC, so A is the last, C is the last. For these we have to find the minimum. Okay, So what is the minimum of this machine A? It is 6. What is the minimum maximum of machine B? That is, again, I'm seeing 5 6 2 3 4, that is 6 again. What is the machine C minimum? Minimum is 4. Okay, now I have to see the condition if the machine A, which is the first machine, because the first machine, middle machine, and the last machine, the third machine. Okay, and the order is A B C. So I have to see the minimum of the machine A. So if minimum of this machine A is greater than or equal to the maximum of the machine B, ओके, जो मैक्सिमम मैक्स यानी कि मिनिमम यहाँ पे क्या है, ए का 6 और मैशिन बी का मैक्सिमम जो मैंने निकाला वो क्या है 6. क्या वो ग्रेटर देन है? ग्रेटर देन नहीं है, लेकिन इक्वल तो है, यानी कि ये कंडीशन ट्रू है. सो इट इज ग्रेटर देन इक्वल, राइट. अगर मान लीजिए ये ग्रेटर देन इक्वल नहीं हुआ, ठीक है, आइदर दिस कंडीशन और दिस कंडीशन कि मिनिमम ऑफ द मैशिन सी शुड बी ग्रेटर देन इक्वल टू मैक्सिमम ऑफ मैशिन बी. मिनिमम यहाँ पे जैसे मिनिमम इसका क्या है 4, क्या वो ग्रेटर देन इक्वल टू मैक्सिमम क्या है मैशिन बी का 6? क्या 4 बड़ा है 6 से? नहीं है. सो इट इज नॉट ग्रेटर. सो दिस कंडीशन इज फॉल्स. फर्ज कीजिए कि ये कंडीशन भी फॉल्स है. अगर ये इफ दिस कंडीशन इज आल्सो फॉल्स, बोथ कंडीशंस आर फॉल्स, देन दिस algorithm is not applicable. I cannot convert the 3 machine into 2 machine. Either of the two, either this one should be true or this one should be true. Either the minimum of machine A should be greater than equal to machine B maximum, or minimum of machine C should be greater than equal to maximum of machine B. Either of the condition is true, then I can convert this 3 machine algorithm into 2 machine algorithm by creating a, if this either of the two condition is true, either this is true or this is true. This is or, not and condition, means either this is true or this is true. अगर एक भी true है दोनों में से, तो फिर मैं कर सकता हूं ये, ठीक है ना. तो क्या करूंगा मैं फिर, I will convert this into 2 machines. So machine, for example, G and machine H, only 2 machines, not 3 machines now. How I calculate? For G, I will add 8 plus 5 to get it. For example, this is 11, then 10 plus 6 16, then 6 plus 2 8, then 7 plus 3, then 11 plus 4, and so on. And for machine H, I will add 4 plus 5, that is C and B I add, then 9 6, then 8 plus 2 is 10, then 6 plus 3 and 5 plus 4 to get 2 machines, and then apply the Johnson's algorithm to solve, which was the 2 machine algorithm we have done, right? So let's come back to this steps here. So what are we saying now? We should be able to understand it properly now. So the optimum solution can be obtained if either both of the following condition hold true. Either both, if either or both means either this one condition or second condition is true, or both are true, then it is okay. If both are true, that's nice. But if one of the condition is true, one or two, anyone, we can convert the 3 machines model into the 2 machine model. Now what is the condition 1? Now condition 1 is that the minimum processing time of machine A, so min of A, is at least greater as the maximum processing time on machine B. That means it is greater or equal to the maximum time of machine B. Okay, if it is so, if the minimum of 1, because if you look at here the matrix, that's why it's written like this, 1, and say this is J, 1 2 3 4, the jobs. Okay, because J is equal to 1 2 up to the n. How many n is there? 1 2 3 4 5 6 up to n. And this is T of 1, this is T of 2, this is T of 3. So if T of 1 J, I call it the second subscript as J, if T of 1J is greater than equal to B ka, but this should be minimum of T of 1J is greater than equal to maximum of T of 2J, because it is 2 for the B. Okay, for J is equal to 1 2 up to n, if this condition is true. Or I can go this way, if minimum of what do you call it, this t of 3j. Okay, if minimum of t of 3j is greater than or equal to maximum of t of 2j, okay, then also I can convert my 3 model machine model to the 2 machine model and apply Johnson's algorithm. If either or both the conditions hold good, then the algorithm can be summarized as follows. So what are we trying to do now will be to convert this 3 machine model into 2 machine model by adding them together, by adding this T1j with the T2j. And same is here for this. I add T3j with the T2j, all of them together. I add this with this, this with this, this with this, this with this, and for next machine I will add this C with this, C with this with this, and so on. Right? So what shall we do? So first step will be to see this condition, whether this condition is true or not. If the condition of from the above is true, then I can go to the step second, or if it is not true, then the algorithm fails. This algorithm cannot be applied on this problem. Okay, so we introduce two fictitious machines, say G and H, with corresponding processing time by adding the two. So T of G of J will be what? So T of I of J plus T of 2 of J. So if you say this one, if I create a fictitious machine which is the G, okay, I call it G of the time of G of J. What will be that equal to? That will be, you have to add time of this T of 1J with the T of 2J, where J starts from 1, 2, 3 and so on. That means adding all of them together, adding these two together, then adding these two together. Okay, so that's what we are doing here, that T of Gi will be T of 1J plus T of 2J for all J's up to N. Similarly, for machine H, because I'm converting two machines, I will convert T of 2J and T of 3J, add them together to get the second this thing, right? And after that you have now the two machine model, and you can apply the the Johnson's algorithm to solve it, right? Like this is an example. So the question says, find the sequence that minimizes the total time required in performing the following jobs on the 3 machines in the order A, B, C. So B is the middle one. Jiska max dekhna hai. We have to see the max of the B and min of the A and min of the C. Then the condition should be that min of A should be greater than or equal to max of B, or min of C should be greater than or equal to max of B. So these are the processing times. So I will calculate first what? I will calculate the min of the machine A, that is going to be 6, min of the machine C, that is going to be 4, maximum machine B, that's going to be 6. And I'm having one condition that min of machine A is greater than or equal to machine B. Yes, 6 is greater than or equal to 6. It's not greater but equal to, it is. So this condition satisfied. I don't need to go for the second condition. I can convert this into the 2 machine model, where machine G and machine H. Machine G's time will be 8 plus 5, 10 plus 6, 6 plus 2, 7 plus 3, 11 plus 4. And for machine C, it will be 4 plus 5, 9 plus 6, 8 plus 2, 6 plus 3, and 5 plus 4. Right? Like this. So I'm adding them to, for G, it will be 8 plus 5, 8 plus 5, as we see here. Then 10 plus 6, 6 plus 2, 7 plus 3, and 11 plus 4. Same way, this will be 4 plus 5, 6 plus 9 for H, and we get the machine with the 13, 16, 8, 10, 15, 9, 15, 10, 9, and 9. This will be my the processing times. And now, then I will apply the Johnson's algorithm. So what is the Johnson's algorithm doing is seeing where is the minimum. If it is minimum on the, if the A machine has a minimum, then assign it to the left side. If B machine is minimum, assign it to the right side, right? So if you are confused by this, you can say, you can use your old question scenario, like we can put up jobs on a this side G and H. Then we had the 1, 2, 3, and 4, and 5, and here I get the 13, 16, 8, 10, and 15. For this guy, I will get 9, 15, then 10, then 9, then 9. then I have to see which is the minimum of all of this. So I am seeing 9 is the minimum, and I'm getting a tie of 9 here 3 times. So I can choose any one of them. Okay, either job 1 or job 4 or job 5. Now this guy has chosen the job 4, so that is why it has put up the job 4 on the left, because I have selected this 9. So that means this job 4 is gone, assigned here. Okay, on the last is oh sorry, first 8 is the smallest, not the 9. 8 is smaller, right? So I have to assign first 3 to the left. So this is gone. After that, there is the 9. So it has chosen the this 9. That is job 4, because from the B side, so it is to be on this side. Okay, it is gone. So who is the next? Again, there are 2 9s now, 9 and 9. So it has chosen this one, so, and put it on the right side. So finished. After that, who is the next? It is a 9, this 9. So job 5, it is to be done on the left side, because it's I'm choosing it from the B, from the second job. So put up this. So this is gone. Now 2 is left out, so that is the 2 here. So my schedule will be 3 2 5 and 4. Okay, so after 3 2 5 and 4, I got the optimum sequence. I can calculate its time, how assignment, from I have to assign first third job, that is this job, which has the 8 unit of time. Okay, on the machine G, and 10 units of time on the machine H. But sorry, the optimum sequence, I got the optimum sequence now. Now this is to be applied on the all the 3 machines. Okay, that means on this table, this will be assigned on this table. Okay, not on on this table. On this table will be required only this combined G and H machine table will be only required to calculate the sequence. So when you got the optimum sequence, now this optimum sequence is to be applied on the actual table, to be applied on the 3 machines, right? So first is the job 3 to be assigned. If you see the job 3, that is here, machine A needed 6 unit of time, so we have to assign it. So assign 0 to 6. Okay, starting from 6, I have to assign the second job, and second job takes here 10 units of time. So 6 plus 10, that is 16. Then after that, assign 5. So 5 is assigned like we were assigning in the Johnson's algorithm for 2 machines. Now sequence is given. Only for sequence, I converted the 3 machine to 2 machine. Now I have to assign the values here. So after 16 to 27, I have to go for job 1. So starting from 27, job 1 takes how much time? Job 1 takes 8 units. So job 1 takes 27 plus 8, 35. Starting from 35, I have to do job 4. And job 4, as you could see, is taking here in the table, job 4 is taking 7 units of time. Okay, so 35 plus 7, that is 42. After this is done, I have to do machine B, assign it 3, but I cannot assign it at a 0 time. I have to wait for 6 units of time. So wait 6 unit, क्योंकि इस वक्त जो जॉब 3 है वो उसको मशीन ए पे काम चल रहा है, तो मैं 0 टाइम पे इसको नहीं असाइन कर सकता मशीन बी को. सो मुझे वेट करना जब तक कि मशीन ए इसको फिनिश नहीं करेगी. ठीक है ना, तो 6 यूनिट्स आई हैव टू वेट. सो आई हैव टू स्टार्ट एट 6, और मैं देख रहा हूँ कि जॉब 3 जो है उसको बी मशीन पे 2 यूनिट्स लग रहे हैं यहाँ पे. सो देन आई कैन गिव इट 2 यूनिट्स ऑफ टाइम एंड सो ऑन, स्टार्टिंग फ्रॉम I finished 22, but job 5 is finished 27, so I have to wait here that much of time. Okay, and then job 5 को जितना टाइम लगता है दे दें, और 31 पे खत्म हो रहा है, तो लेकिन 35 पे वेट करना पड़ेगा. this much of time, 4 units of time I have to wait here. Then assign these values the same. Then the machine C, so machine C cannot start the job at 0, because 0 टाइम पे जो थर्ड जॉब थी वो A machine के ऊपर थी. I cannot start at 6 because up to 8 it is engaged with the B. So after 8 only I can start. So its waiting time upfront is 8. C का waiting time पहला जो है ना 8 है, इसका पहला क्या है 6 waiting time. Up to 6 I cannot start. And इसका waiting time पहले नहीं होता, इसका end पे waiting time होता है, because it has to wait for this much कि जब तक finish नहीं होगा, right? So this is my total time. Okay, total time elapsed time is 51 hours. Okay, idle time machine A and B, you can see it is 51 minus 42, that is going to be for the machine A. For machine B, it's got to be, firstly I have to wait for 6, so 6 is to be added there. Then 16 minus 8, 27 minus 22, 35 minus 31, 42 minus 40, calculate that much. It is done here, as you could see. Okay, then for that is 31 hours. Then for this machine I have to wait firstly the 8 hours upfront. Then you have to wait 22 minus 16, 31 minus 31 0, 40 minus 36, 45 minus 44. So whatever that time is, that is to be added, and it's equal to 19 hours. So machine C waits for 19 hours. Okay, hopefully I think you are getting it properly. Now this is another question here. You can just see this question and try to solve it yourself. Just see the solution. I'm sending you this PDF also. You can pause the video, write this, and try to see how we got this G and H by adding them together if the condition is satisfied to get the optimum sequence. When the optimum sequence is there, then apply for machine A, machine B, and machine C, same sequences. Only try to see that you don't overlap the time slot with the other machine. You have to wait, B has to wait for A, and C has to wait for A as well as B, and then calculate the idle time, and total time is 49 here, right? If you have questions, you can ask me on a WhatsApp group all the time, anytime. But you need to get the copy and pen, write it, watch the video, and watch it again and again till you get it, and then ask the question. You can always ask me a question. I'm always open for the questions. You can ask anytime the question. I will, inshallah ta'ala, reply all the questions and satisfactorily answer them, inshallah ta'ala. But the thing is that you have to open up the copies and pens and write, and then try to remember formulas, try to remember things. It's very easy otherwise. It's very, very easy, but you have to actually practice. Then and only then you can be perfect in this. Okay, then see you next time. Ma salama.